So last three lectures we've been looking at the sinusoidal steady state response of circuits and how to analyze that response. For all the analyses we had assumed that the input source had a single frequency. Now this lecture we look at circuits under sinusoidal steady state, but what happens to the circuit as the frequency of the input signal is changed over a wide range. And this is called the frequency response of circuits. So that is what we'll study in this lecture, and in the process we'll do this through circuits which are called as filters. So let's start with this simple circuit. We have seen this circuit before. So it's an op amp, there's an R2, R1, but now there is a capacitor connected in parallel with R2. In fact, we had derived VO given some input voltage source for this circuit. So I'm just going to write the answer for VO and then we'll study the answer. So VO over VI, the output voltage divided by the input voltage in the frequency domain is given by minus R2 by R1 into 1 by 1 plus j omega R2C. This function in the frequency domain VO over VI is often called the transfer function of any system. So the output divided by the input is called the transfer function. It is variously represented as A or H sometimes. I think the book perhaps calls this H. I am calling it A because it is also the voltage gain of this circuit. So we can write this transfer function as a magnitude and a phase. So the magnitude is R2 by R1 into 1 by square root of 1 plus omega squared R2 squared C squared, and the angle is tan inverse minus omega R2 C plus 180 degrees. That 180 degree comes from the minus sign. What we are going to do in this lecture and the next is look at the magnitude and how the magnitude varies with the frequency changing. Alright, so that's what we are going to do. Now frequency responses are very fundamental to characterizing electronic circuits and systems. Why is that? Because as soon as we have energy storage elements L's and C's, the circuit responses, the currents and voltages in the circuit become a function of frequency. As we have seen before, if a circuit has only resistances, then there is no frequency dependence, and if the input voltage source is or a current source is sinusoidal, then all the currents and voltages are in phase with the input voltage or current source. If the circuit is completely resistive, there is no delay in the circuit. As soon as you have inductors and capacitors, you have delays, and delays, as we saw in transient in the response, another way of talking about delays is to say that the response of the circuit with frequency changes. So for example, if the frequency is very high, which means that the voltages and currents are changing very quickly, then the inductor and capacitor don't necessarily allow the currents and voltages to change very quickly, and therefore the inductor and capacitor change the response of the circuit at high frequency. So that's what we'll study now mathematically. Now one way of studying frequency response is through what are called as Bode plots, named after a scientist or an engineer called Bode, and they are plots of the magnitude and phase as a function of frequency. So as I said, we'll only look at magnitude plots in this course. Bode plots are also actually piecewise linear approximations of the actual plot of the magnitude versus frequency. So we'll do the piecewise linear approximations. Alright, so we'll look at this circuit. So this circuit, and we'll look at the magnitude R2 by R1 divided by square root 1 plus omega squared R2 squared C squared. So that is the magnitude of A, and I'm writing this as some A0, which is R2 by R1 divided by square root 1 plus omega squared by omega 1 squared, where omega 1 is 1 over R2C. So that this is a more generalized function, and it does not need to be for this specific circuit. This is just a transfer function for which we want to study the frequency response. Now, as we'll see by the end of this lecture, frequency responses are plotted on a log-log scale. So what we want to do is we want to plot the mod of A as a function of omega. That is a gain Bode plot, the response. The way this is plotted is by taking logs on both sides and then in fact multiplying by 20. So 20 log of A with a base 10, it will be the left hand side, and we'll do the right hand side in a minute. This 20 log of A to the base 10 is called the dB voltage gain. So when you see things being referred to in dBs, this is the definition. The power gain as opposed to the voltage gain is defined as 10 log of P out by P in. The reason being that power is, in some abstract sense, is a square of a voltage, and so if you write this as V squared, V out squared by V in squared, then that square going out will make it 20. All right. Just a little note about dBs. So you may have come across audio systems and speakers being referred to in dB. So you say this speaker has a 40 dB output, or that speaker has a 50 dB output. Now when one talks about a dB output, dB is actually a dimensionless quantity. So let's go back here. Where do I go back? Here. dB, power or voltage gain, is a dimensionless quantity because it's a ratio of two powers or two voltages. But nonetheless, you say, well, the speaker has a dB output of 40 dB. What it refers to, or it means, is that powers as specified in dB are referred to a 1 watt input. Alright, so when I say that I have a 20 dB speaker output, it means that 20 dB is equal to 10 log, 10 because it's power, of the output of the speaker divided by 1 watt. So that 1 watt is assumed. So if this is what is the output, then 20 dB by 10 is 2, and then 10 raised to 2 is 100, and so P out is equal to 100 watts. So 20 dB refers to 100 watts. If it was 40 dB, that is double, so this will be 10 raised to 2, so that will be, 10 raised to 4. So that will be 10 raised to 4 watts, 10 kilowatts, alright. So that's how it goes. Alright, so let's do the Bode plot. So this is our transfer function. So we take 20 log of both sides, so we'll get 20 log of A equal to 20 log of A0 minus 20 log of this quantity in the denominator. And when you take the square root out, so we can write this as minus 10 log of 1 plus omega squared by omega 1 squared. Now the way we plot, so what we want to do is we want to plot this 20 log of A as a function of log of omega, as we'll see. And the way we plot this is we'll approximate this expression for various ranges of frequencies. Alright, so let's see how we'll do it. Alright, so we say, well, let us look at this function for omega frequencies much less than omega 1. Omega 1 is 1 by R2C. So that's a known quantity. So we say, well, what happens to this expression if omega is much less than omega 1? Alright, so that is kind of our starting point. So we say if omega is much less than omega 1, then 1 plus this can be approximated as simply 1. If omega is, let's say, 100 times or even 10 times less than omega 1, we ignore this term, so you get 1. And then we get 20 log of A equal to this, and this is log of 1, and log of 1 is of course 0. So we'll just get 20 log A0, which is 20 log R2 by R1, because A0 is equal to R2 by R1. So what we say is that, well, at very low frequencies, omega much less than omega 1, the voltage gain of this circuit is just nothing but R2 by R1, which actually we can see qualitatively that at very low frequencies, this capacitor basically behaves as an open circuit. That's one way of saying it. Another way of saying it is 1 over j omega c. If omega is very small, 1 over j omega c is very large. And so you have a very large impedance connected in parallel with another impedance. So the smaller impedance dominates, and so we basically ignore this, and all we are left with is the R2 by R1, which is nothing but just a simple inverting amplifier. So at low frequencies, this circuit behaves as an inverting amplifier with a gain of minus R2 by R1. Okay, now let's look at what happens when omega is equal to omega 1. So when this is the case, then of course this is 1 plus 1, so that is 2. So we substitute that here. So this is 1 plus 1, 2. So square root of 2, which is 10 log of 2. And 10 log of 2 turns out to be 3.03. So it is almost always written as 3. So what this is telling us is that at omega equal to omega 1, the voltage gain, which was at low frequencies 20 log A0, drops by 3 dB when omega is equal to omega 1. Alright, so the frequency omega 1 for this transfer function is often called as the minus 3 dB frequency, because at this frequency the voltage gain has reduced by 3 dB from its low frequency value. This frequency is very important in characterizing on any system, and it's also often called as a corner frequency or a cutoff frequency. We will discuss both of these in a few minutes. Alright, then we say what happens if omega is much greater than omega 1. So we saw omega much less, equal to, now we say much greater. So if this is much greater, then we say, well, compared to omega by omega 1, we ignore the 1, and so we make this approximation. And then we say 20 log of A is equal to 20 log of A0 minus, so let's go back. So what happens here? This 1 can be ignored. The square root cancels the square. So we'll get minus 20 log omega by omega 1. Right, so minus 20 log omega by omega 1. So if we can write this as y equal to mx plus c. C is a constant, y is our y-axis, x is our x-axis. Actually log omega is the x-axis, but it really doesn't matter because it's just a fraction. So and m is the slope, and the slope is minus 20. Alright, but the slope is referred to as dB per decade. It is actually not a dimension because neither dB nor decade are dimensions, but this is the way it is referred to, and we'll see why or what is the logic of this. What this means, a slope of minus 20, is that when the frequency increases by 1 decade, that is a factor of 10, the gain decreases by 20 dB. Decreases because there is a negative sign. If this was plus, the gain will increase. So let's see how this comes about. So we say, suppose at some frequency omega x, the gain is ax. Alright, and omega x, I'm assuming, is much greater than omega 1. And then let us say that at a frequency 10 omega x, the gain is some ay. Alright, then we can use this equation to write ax and ay. So we say ay minus ax. So for ay we say 20 log a0 minus 20 log. So ay corresponds to 10 omega x, and minus ax is minus 20 log a0 plus 20 log omega x. Ax corresponds to omega x. Alright, so we subtract, so these two cancel, and then 20 log of omega x by omega 1, and then minus, so this will become omega 1 by 10 omega x. So we get this, and the omega 1 cancels, omega x cancels. So we'll get log of 1 by 10, which is minus log of 10, and log of 10 to the base 10 is 1. So you get minus 20 dB. So what we found is that when the frequency changes by a factor of 10, the gain changes by 20 dB when this is satisfied, this condition is satisfied. So you say the gain drops at a slope of minus 20 dB per decade of frequency. Incidentally, 20 dB per decade is also equal to 6 dB per octave. Octave is doubling of frequency. A decade is 10 times, octave is 2 times. So you can prove yourself that if this was, instead of this 10, this was 2, then of course this will be log of 1 by 2. So minus log of 2, and log of 2 is 3. So 20 times, now log of 2 is 0.3, so 20 times 0.3 is 6 dB. That's how you'll get minus 6 dB per octave. Alright, so let's look at this qualitatively. So I saw that at low frequencies, this is a very high impedance and we can ignore it compared to R2, and we get a constant gain of minus R2 by R1. At very high frequencies, 1 over omega c becomes smaller and smaller and smaller, and therefore this dominates over R2. And then if you think of very high frequencies, then this impedance is very small, and the gain of this circuit is, so VO by VI is basically the Z of this combination divided by R1, and Z is dropping because 1 over omega c is dropping, and therefore the gain is dropping also as a function of frequency. And if you go to extremely high frequency, you say, well, the capacitor acts as a short circuit, and if this is a short circuit, then there is no gain at all, right? The VO. So as C tends to 0. No, I'm sorry, as omega, not C is constant, as omega tends to infinity, 1 over omega c tends to 0 and VO tends to 0. Alright, so that is what is happening. Now let's make a plot of this. So this is a table summarizing what we have found. So for omega much less than omega 1, this is the gain. At omega 1, it is reduced by 3 dB, and for much greater than omega 1, we can write the gain as 20 log A naught omega 1 minus 20 log omega. So if you are to plot dB gain, which is 20 log of A versus log of omega, then we'll get a minus 20. So this is a plot of dB gain 20 log of A as a function of log of omega. So what we find is that for very low frequencies, this is a constant, and at high frequencies, this drops at minus 20 dB per decade. At omega 1 is when the transition occurs from flat to dropping, and this is the reason omega 1 is sometimes called the corner frequency. It is a frequency at which the slope of the line changes. By the way, the corner is only an approximation. As I said, this is a piecewise linear approximation of the actual Bode plot or the actual frequency response. The actual frequency response does not have corners. It's a continuous. So it will, in fact, it will be minus 3 dB at omega 1, and it will kind of join asymptotically these two at low and high frequencies respectively. This is also, as I said, omega is also sometimes called the cutoff frequency, because what we see here is that this circuit provides some gain for low frequencies, and at high frequencies it does not okay, let me put it another way. Let's say I have many signals applied simultaneously to this circuit, and some are at low frequencies, some are at high frequencies. All the low frequency signals will appear at the output multiplied by the voltage gain of the circuit, which is R2 by R1. All the high frequency components of the input will get attenuated or will experience a much smaller gain compared to the low frequency output. So they will be here depending on the frequency, and the output magnitude of these voltages applied at the input will be very small. So for that reason, this omega 1 is called the cutoff frequency, to say that for frequencies above omega 1, any signal that is applied at the input, the output will be attenuated, or it will be cut off, quote unquote. So as you may know, this circuit is called a low pass filter because it allows low frequencies to pass through, and it does not allow higher frequencies to pass through. All right. Okay, so this is the actual, so this is, and I did it in a circuit simulation. So this is the actual frequency response of the same circuit for some given value. So it is flat at low frequencies. It drops at 20 dB per decade at high frequency. In between, there is a continuity. The Bode plot, or the approximate Bode plot, would go flat up to the corner frequency and then start dropping. By the way, this dashed line is the phase plot. So the solid line refers to the left axis, which is in dB. The dotted line refers to the right axis, which is the phase in degrees. But as I said, this course will not look at the phase plot at all. All right, acha, one more thing I wanted to mention. So this plot has y-axis in dB, x-axis is a log axis, right? So you have 1 hertz, 10 hertz, 100 hertz, 1 kilohertz, 10 kilohertz. This is a log axis. Now, why does one plot a frequency response on a log scale? Why not on a linear scale? So here is the same plot on a linear scale with an input applied of 1 volt. So the output is plotted from 0 volts to 9.9 volts, where it is going to up to 10. So the voltage gain I had made was 10. And the x-axis is the frequency. But what you observe is that if I have a frequency, let's go back, the frequency, let's say varying from 1 hertz to 10 kilohertz. If I plot this on a linear scale, then all I see is 10, 8, 6, 4, 2, and then this will be close to wherever, somewhere, well, what is happening here? Around here, the frequency changes from 1 hertz to 1 kilohertz, all right? And so the information for low frequencies gets bunched up in a very small interval of the x-axis, and one really can't see what the circuit is doing at low frequencies. But here I can see clearly what happens at 1 hertz, 10 hertz, 100 hertz, and so on. So if I want to be able to see, and this is of course true for any variable that is varying over large magnitudes or large orders of magnitude, right? This is 1 to 5 orders of magnitude. This is varying over. When the frequency or any variable varies over such a large range, to get a clear picture of what is happening in the lower side of the range, it is better to plot on a log axis. All right, so that is why frequency response are plotted on log axis. All right, now let's look at the other circuit, the high pass filter. So this was a low pass filter. It allowed low frequencies to pass through. Now how do we build a high pass filter? So for a high pass filter, we put the capacitor here rather than here. We put it here. So first let us look at this qualitatively. So here what is happening is, for low frequencies, the capacitor acts as a very high impedance. And so this total impedance of this leg of the circuit is very high, right? Because omega is low, 1 over omega c is high. This is high, and the gain is R2 by this magnitude of this Z. And the Z is high, so the gain is low. So you'll get low gains at low frequencies. At high frequencies, the capacitor starts offering a lower and lower impedance, and it becomes much lower than R1, and so one can ignore it, just basically a short circuit. And so the voltage gain becomes minus R2 by R1. All right, so let us go through the mathematics of this. So one can derive the transfer function. So this is A is R2 by Z, where Z is the series combination of R1 and 1 over j omega c, which can be written as 1 plus j omega c R1 by j omega c. And we substitute that in the A expression. So you'll get minus R2 by R1 j omega c R1 by 1 plus j omega c R1. Now I can rewrite this as omega by omega 1, where omega 1 is 1 over CR1. So you can see that the corner frequency here is going to be omega 1, which is 1 over CR1. Earlier it was CR2. Alright, the other thing we notice is that in this transfer function there is an omega term in the numerator. In the low pass filter, the omega term was there only in the denominator. So this is a characteristic of high pass functions, that there will always be an omega term in the numerator. And so we write the magnitude as R2 by R1, omega by omega 1, square root of 1 plus omega squared by omega 1 squared. Now again we will go through three regions of omega: 1 omega much less than omega 1, omega equal to, and omega much greater. And then we make approximation. So this is a function. This is written in the dB form. So 20 log of A is equal to 20 log of A naught plus 20 log of omega by omega 1 minus 20 log of square root of all this. And then we do this for three different ranges of frequency. So for omega much less than omega 1, this is approximately equal to 1. So here we substitute omega by omega 1 stays. This becomes approximately 1. So 20 log of 1 is 0. And so this we can write as 20 log omega from here plus 20 log A0 by omega 1. And so we get 20 log of A directly varying as 20 log of omega plus a constant. So again this y equal to mx plus c, and the slope now is 20, but it is a positive slope. Alright. So the gain will increase as a function of frequency because of this. Where was this? Because of this term, the one on the numerator, this second term. At omega equal to omega 1, this is equal to 2. So we substitute that here. So this will be log of omega or omega 1 is 1. So 20 log of 1 is 0 minus, this will give us a minus 3 dB. So here at omega equal to omega 1, the gain is 3 dB less than 20 log omega A0. At high frequencies, this is equal to, we can ignore the 1. So we got omega squared by omega 1 squared. And so the last term will be, let's go back. So the last term is this, and that becomes simply minus 20 log omega by omega 1. This and this cancel, and so we get the gain as 20 log A0. So at high frequencies, the gain becomes a constant. At low frequencies, the gain is increasing, and then it becomes a constant. Alright. So if you make a Bode plot, the gain increases at low frequencies, it is a constant at high frequencies, and in between at omega 1 it will be actually minus 3 dB. On this approximate plot we just show two straight lines. This is a high pass filter. It allows high frequencies to pass through, and it does not allow low frequencies to pass through. Alright, and this is the actual simulated plot. So again same thing. High frequencies are passing through, low frequencies are not passing through. The dotted line again is the phase plot. Alright, so this is the end of this lecture. Next lecture we will look at more filters which you will use in your assignment.